So this is essentially where we left off. We were talking about hemoglobin and doing these binding curves. In particular, we were talking about the small molecule, which is the glycolytic intermediate. We'll talk a lot about this, or the glycolytic intermediates like BPG, a lot next semester because they're common metabolites. Okay? The BPG actually helps regulate oxygen binding in vivo. What it does here is it's going to promote or stabilize the T state. So therefore, it helps release the oxygen under physiological conditions, much more likely. And this is the example to where if you actually, for a healthy adult, if you remove the BPG, which is what this is showing here, notice it becomes more and more and more hyperbolic, which is really important. And the 1/2 value, the K1/2 value, goes to non-physiological concentrations for O2. So what I'm saying by that, what I mean by that is this, I don't know why they didn't do it for the 0. See, we would actually have to go, and I'm not very good at doing a straight line, but this is like less than 1 kilopascals, which I don't think of kilopascals. I wish I would have put it in millimolar. But 1 kilopascals, less than that. And you can see that is not the concentration of oxygen that you normally have in your tissues. And so therefore, if you don't have BPG around, you would never release oxygen at those physiological levels. And so you would potentially, it would be fatal. Okay. And so make sure that you really understand how to read and do these kind of plots and graphs, because they're very important, not only for this chapter, but also just in general in future, because we do a lot with graphing for enzymes, and we also do some next semester when we start talking about like how it is that you can have common metabolites and intermediates with different metabolic pathways and different enzymes, and something, like one tissue for the other tissue, and so they use the plots a lot of times to talk about that. One other thing is I do want to remind everyone, I think I don't remember if I told about in this class or not, but they're releasing the schedule. We are offering a biology specialization or chemistry specialization class next semester called Enzymology that I'm going to be teaching, which is going to go into more detail, and we're teaching it primarily for those for the biomedical aspect, but you can count it either towards biology specialization or your chemistry minor. You have to choose one or the other if you choose to do a chemistry minor. I don't have it memorized what that course code is. It's got a new course code number. It's a CHEM. I think it's a 3000 level class. Just a little FYI. Okay. Oh, and one other thing about next semester. One thing that's brand new because they run out of rooms in this building. Biochemistry lab. It's still going to be a Monday and Friday lab. Like it's no longer going to be in the mornings. It's like late in the day. I'm going to say like 4 to 5:50 or 3 to 4:50. It's 2 hours on Mondays and Fridays, but late in the day, like after capstone. And so this is a little FYI for you. I had to do a double take. Right now, it's still listed wrong because whenever I got it back, it says a Monday, Wednesday, Friday class. I was like, what? I've never done that before. But no, Dr. Strauss did. Somebody over in the registrar's office must have typed it in correctly. Okay. But yes, we do go over these kind of things all the time. So especially now that I've had a child, now that I've fathered a child, this is really cool. But it's cool before too. It's just now I have more of an appreciation for it. So there are multiple isoforms of hemoglobin, and the maternal one, for whatever reason, they call it HbA, which whenever this got converted over, I think I guess it's the same. Okay. Versus the fetal version isoform, which is called HbF. And then as you age, as you get older after birth, then the relative amount of HbF decreases transcriptionally, and your HbA version increases transcriptionally, okay, for regulation. But what's really cool about this is make sure that you can explain the rationale and understand like what's going on here, like why this really matters. So if we just wanted to look at this, once again, whether you say degree of saturation or theta, or you went from 0 to 100%, that's not important. If you use partial pressure of oxygen, like this time they're using torrs versus kilopascals, or if you use millimolar, usually I use concentrations in molar or millimolar. It's really the shape. You see what we would have called the wild type version right here. But what's one thing that you can notice about the fetal hemoglobin? Does anything make a statement about it? It has a higher binding affinity for oxygen. Okay, and that's true at all concentrations of oxygen. Why do you suppose that's very important physiologically? How does the fetus breathe? And don't tell me carefully. Where does the fetus get its oxygen? From the mother. So literally what happens is, as the mother breathes in through her lungs, the oxygen concentration increases, so it's going to bind. As it travels to the fetus, where the oxygen concentration is lower, a higher percentage of the maternal hemoglobin is going to give up its oxygen, and this has a higher affinity for it already, so it will bind the oxygen. So the fetus will rob the mother's hemoglobin, so to speak, at that concentration because it has a higher affinity. And that's true to all concentrations of oxygen. So that way the fetal hemoglobin has a higher affinity. Now it should also make sense that as the child is born and gets older, then you're going to want to revert back to, or not revert back to, start to express the wild type, the HbA version. So that way your lungs as the child is developing is more prone, you're in the aerobic environment, then it's going to be easier for it to breathe naturally. Okay, you want the one that combines BPG. The way that happens actually is the fetal isoform doesn't bind BPG as tightly. It has a lower affinity. So there's less BPG bound, so therefore it binds oxygen more tightly. Okay. There are lots and lots and lots of abnormal human hemoglobin. Okay, this is just three different ones. If in the suggestive problems, there's at least one of them, which if you got the most recent edition of the book or the solutions manual, you want to check to see what it correlates to for the 6th edition. Because what it does is it lists like 6 or 8, a whole bunch of the different ones. So some have really funny names like Cowtown and things like that. And it gives you a sense of what happens. And you have to be able then to explain either the binding curves or the physiological response that you would see out of this. So the very first thing that we're going to talk about is HbS, which is one of the more common of the hemoglobin mutants. And the HbS is a single point mutation of a valine for a glutamate. Okay. And what that means is that's at the 26th position. Remember, it's on the beta sheet. It's all alpha helical, but it's on the beta subunit. It's just a thing. This is the one that causes sickle cell anemia. What happens with sickle cell anemia? Why is it called sickle cell anemia? Right. And so it looks like a sickle, and not as in a popsicle, a different type of sickle. All right. So, which is like I've had people ask me like, what do you mean by sickle? It's a cut wheat, to cut grass. It's the thing that's on the Communist flag of Russia. So, not the old Communist flag of Russia, I should say. The new one is red, white, and blue. And so what happens is it forms like a little stickiness to it as well, and they don't do that transition with oxygen binding. A little historical side note, does anyone know why? Why does it stay around if it's bad? It can be very painful, I've been told. First of all, what ethnic group tends to have a higher population of sickle cell anemia than any other? People of African descent, not just African Americans, people of African descent, but why? As well? Especially if you are heterozygous. Like if you are homozygous for the sickle cell, then it's worse than if you're heterozygous. It has a much less affinity for contracting malaria. If you have, one wild type version of the allele and one HbS version of For HB Savannah, it's a glycine to valine mutation. And you can imagine, what does glycine look like? What is the R group on glycine? It's a little hydrogen, valine's really big, and so because of this, it actually disrupts the ability for the conformation upon oxygen binding, and so it is a type of anemia, since oxygen can't bind as easily. And there's one called HB Milwaukee, and here we have a valine to a glutamate. So valine, what kind of side chain is a valine? Non-polar, whereas glutamate is not only polar, but it's acidic, and it actually forms an ion pair with the heme iron. So you can imagine. So we have glutamate. There's the backbone. 1 carbon, 2 carbons. Make sure you know how to draw glutamate. And in reality, I draw it this way, but that negative charge. Remember, think back to organic chemistry and chem. It's going. There's resonance there between the two oxygens. But it actually stabilizes iron binding. Which you'd think, well, that's fine and dandy, oh, yay. So there's the heme there, you're going to bind the iron, iron's going to bind type, so why not? But for those in neurochemistry, what can you point out? What's the one thing, if you're in neurochemistry, we'll talk about smart looking people, but, and you just read this, what's the one issue, the one problem with that statement? See, this isn't a neurological issue. We've talked a lot about iron recently. What's the problem with this iron? It's Fe3. Okay? Whereas what's the biologically relevant iron? Fe2. Fe3 is, your body actually has a large population of Fe3. That's the form that we use to store iron inertly. It's called labile. For those in biochemistry, not in neurochemistry. And so Fe2 is the one that can form reactive oxygen species. However, the Fe2 is the one that's required to do the correct binding of oxygen in your heme. And so, since the Fe3 prevents O2 binding and causes a disease or a condition called Methemoglobinemia, not Methemoglobinemia, no, and it results in people being blue. They have a blue pallor to their skin. And unfortunately, I think that this does it justice in this. I can't really tell this more gray here, but we can see the fact that there's an abnormal pallor to their skin. But they do have a blue look to them, to their skin. And there's a common, one of the big cases, like historically, are called the Fugates. And I can't remember, I want to say it's Kentucky and West Virginia, I think. Kentucky, West Virginia, maybe it's Tennessee, Kentucky, West Virginia, I don't know. It's right around that part of Appalachia, with the whole Hatfield and McCoys, that the Fugates also around. And because the population years ago was very low, there did tend to be a lot more close breeding of, related cousins and things. And so there's this large population of the Fugates, and a large population of them had Methemoglobinemia, and so there's only 2 people. At least back that time, of course now I don't want to see died out, it's been watched out a little bit more. Yes?
Are people with this condition not able to participate in sports and things that require high oxygen?
I don't know the answer to that. Well, I would say that they would be suffering from anemia in general, so they would have to be careful. Okay. One thing about it is it's obvious. When you are suffering from this condition, you're going to color it wrong. Okay, I should say wrong. God made you that way. Color differently. So I don't know about you guys, but did you ever, as a little kid, sing the song of Jesus Loves the Little Section of the World? Which don't get you started on how absurd the song really is, but you can now actually. Wow. Yeah, so that's kind of faith injection of sorts. All right, this last little bit, we're just going to talk about protein-ligand complementarity. Please note, this is complement with an E, not complement with L-I-N. Complement with an I is E that nice today. Well, thank you. Whereas complement with an E means that they are structurally, how they fit together like lock and key kind of thing. They fit together well. Okay. So usually, unlike the way that we talk about oxygen and carbon monoxide and heme, which is the prosthetic group binds and everything, many times we're talking about interactions that are due to structural complementarity. And so one way to think of that is like receptors binding at ligands binding at the receptor. So for example, a histamine binding to the histamine receptor. Okay. Many times we use the term induced fit, and we'll talk, hopefully we'll have enough time in the next chapter to talk a little bit about how that's not 100% correct, but it's more correct than lock and key. Okay. And the quote-unquote textbook example, which really is a textbook example we're talking about here, are the whole idea of antibodies and antigens, which is an epitope and the way that they interact with each other. Once again, this PowerPoint's already available on MyFire. I used to go into a lot more detail with this because we didn't offer immunology, and in the other classes they didn't cover immunology in very much detail at all. But now that many of you have taken the actual immunology class, or I think now in genetics and some luck and stuff like that, they started to pick up on these points. I don't cover, I'll go more quickly than before. On your own, you can always review. But just some of the terms that get used around are a lot about, we have leukocytes, which are white blood cells, and there are different types. We have macrophage or macrophage, depending upon, it's pronounced both ways, depending upon your proclivities. And then there are the lymphocytes, which are B and T cells, and they get their names, I don't know, I assume you guys don't know why, but they're called B and T based off of where development occurs. Okay, B is in the bone marrow, T is in the thymus. Okay, the part that I've noticed, and I even get this, in my haste, sometimes we'll speak incorrectly between the antibody and antigen or epitope. Okay. All right, antigen is whatever's going to elicit that immune response. The antibody is what's going to come and bind to that. But the part of the antigen that the antibody recognizes is called the epitope. Okay. So that's why it's also called the antigen. Sometimes I've heard people use antibody, they really mean antigen, or they'll call it epitope, and they really mean antibody, and those are how they go together. And then you've heard of the antibodies, are also called immunoglobulins. You usually start with IG, whatever. You probably heard the most with IgG. I can't remember why I put these in different colors. I think it's because IgM and IgA are not your what's the shape that usually is written out for these, which is a little off. But what shape, how do they draw these? And you're just going to draw a little cartoon of IgG. What does it look like? What does an antibody look like?
Is it a Y?
Y, they always draw this Y. We're going to find that. It's not quite a Y. They always draw a Y. Well, the IgM and IgA is actually, they're actually, it's a big, huge quaternary interaction. So then we have this whole idea of polyclonal versus monoclonal antibodies, and it has to do with whether or not, how many different epitopes and stuff that they bind to and that they recognize as suspects. Okay. So their specificity. We will go a little more, because this is going to play into what's coming up next, go into the constant, variable, and hypervariable regions. And what that means. Okay. Oh, here's just a little table from your book. All right, this is the important part. This is the reason why they always like to draw it as the Y. Like I said, it's definitely an oversimplification. We're going to look at the actual crystal structure of one in just a moment. First of all, these are huge. These are not these little tiny things that I think that many times are noticed. So if you notice, there's these V's and C's, and there's an L and an H subscript. All right, so the C stands for the constant domain, which is just like the name implies. They do not vary in their composition, versus the V region means it's a variable domain. And it's these V regions that actually will recognize the epitope. And H would be the hypervariable, They actually don't show the region. But the hypervariable region are the parts where the actual epitope determinant will be binding, or the antigen determinant binds. Okay, so that's why they're hypervariable. That's where they change the most. Mm-hmm.
So it's actually 4 different polypeptides?
Yes. In the final post-translational formation of the quaternary structure. Mm-hmm. That is true. There is 4. Now, the L's and the H's stands for light and heavy change, which has to do with their molecular weight. So if we notice the L's, this is a relatively small polypeptide. This one's much larger, and so it's the heavy chain. And then for the IgG and IgE and some of these, they look like this quote-unquote Y shape. They're only held together by disulfide bonds. The disulfide bonds occur between what amino acids? Cysteines. Okay. The arms, so quote-unquote arms of the Y is where the antigen would be binding. Okay. And I don't think this book, the chapter in this chapter is the one that goes over like how I don't think that it goes over how that the antigens are made. Not made, how the antigen binding site is made, I should say. Alright, so then there are some like M. Oh, I'm sorry, I skipped over this. This is the actual structure. Which if we were able to rotate it, you gotta look at it rotating, it's much more twisted than a traditional Y. But you can see, if these are glycoproteins, they do require sugars to be consumed. So it shows that they have carbohydrates. And so once again, the hypervariable region would be up here. Okay, because that's where the actual epitope would be binding. This is IgM. Okay, IgA and M are actually both pentamers of the individual quote-unquote Y's, and so they're much, much larger. And that little tiny chain in the middle that helps hold it together is called the J chain. Okay. All right. So I actually do like to show this one because to me it looks like a hand. I don't know if it comes across very well. It looks like it's got a thumb and 2 fingers. So they show it without the antigen bound and then with the antigen bound, but not shown in B. And so what they've done is they've just hidden this little stick figure here. And so if you look, red and blue, you look and you can see where the positioning of the thumb to 2 fingers changes upon binding. And so it literally does cause this conformational change, this induced effect. And so this is really cool. So how can we take advantage of this? They are highly, highly, highly specific. So there's a term called KD, which we actually go into detail. I don't know, we don't really talk about KD in this chapter. They mentioned it, but they don't really talk about it. Next chapter will actually explain what KD is. I'm already mentioning the fact that you can make monoclonal polyclonal antibodies and utilize what's so important. Make sure you understand ELISA because it's used all the time. ELISA, and then immunoblot, which one of the most common blot would be we're talking about the Western blot. Because we only have like a minute left. So I just wanted to show this, and then on your own you can finish reading about the muscle and the triple lesson. Like I said, that should be reviewed because all of you should have EMP at this point in time. But the way that this works with the ELISA is you have to have a secondary reporter. So whatever it is that you're testing for, like let's say glucose is usually the example that I like to give because most people understand it. So you put your sample down here, and then you have your antibody that would be specific for the glucose, but it's a silent one. You can't actually see it directly because it's really expensive to make specialized antibodies that are already fluorescent or radioactively labeled. Then what happens is you buy a generic either fluorescent or radioactively labeled. This one's enzyme linked, this is ELISA. One that is an antibody that's non-specific. I shouldn't say non-specific. It's specific for the part of the antibody that doesn't change. And so therefore, it actually is recognizing the antibody that recognizes the antigen that you're looking for. And then the one for ELISA, covalently attached to the end of that is an enzyme that will give a colorimetric response. Okay. So meaning it'll change colors. So the darker the color change, the higher the concentration of the original antibody here. No, I'm not an antibody. See, I said it there. The original antigen there. So this is just, well, come on. This is an actual picture. I don't know how they didn't put the key on this one. Normally when we would set up ELISAs or radiometric assays like this, we would always have two controls. We'd have a positive and a negative control. We would always do them in the corners. So I'm assuming that this is a positive control because you see it is yellow, and that this is the negative, which is white, or this one. It could be one of these two. We would use, normally out of habit, I would do the first two, but usually we do but I don't know how to do that. But we would always include both a positive and a negative control. And then you can see here like there's more yellow in this one, so therefore it's going to have a higher concentration of whatever it is that they're testing for versus this one over here, so on and so forth. Okay, so I'm going to go ahead and